At this time, I'd like to welcome Dr. Schwartz from Ohio State University as he provides his final project presentation on CERTIT Project ER-1684 titled Semi-Passive Oxidation-Based Approaches for Control of Large Dilute Groundwater Plumes of Chlorinated Ethylenes. Frank, I'll turn it over to you.
Okay, that's great. Yeah, thank you everybody for attending, and again, thanks for the opportunity to do this debriefing here. I'd like to acknowledge my colleagues here who are on the line as well. Utko Solpuker, who did much of the work here at Ohio State, and Dr. Lee from OU, who did a major component there at OU. And there are times in the talk then when both of these folks will have things to talk about, and I think we're reasonably choreographed here. So let me begin. This is our project team here on slide number 2. And so there's me, Dr. Lee, Dr. Stephen Lauer. He didn't end up participating as much because we ended up with a microbiological component initially, and then we veered away from that. Dr. Solpuker was a postdoc at the time, and then we had various students participate. Jared Hawkins here at Ohio State. NSOC had Pam Olson and Neha Gupta at OU, and right now we still have an undergraduate student who's doing a student thesis as well. So slide 3 here gives the background of our basically our project. The statement of need really is to talk about a cost-effective technique to remediate large and dilute plumes, and the real focus was on deep plumes. So the typical array of contaminants of interest at DOE sites are the chlorinated solvents, PCE, TCE, DCE, and so on. And these are present at many sites, estimated at 3,000, depending on various numbers and so on. And I think our focus was on large plumes, and the picture at the right is an example of one of these plumes. And this is a plume of chlorinated solvents that's present at former Otis Air Force Base. And again, the particular focus was on plumes that tend to be deeper, where other remedial technologies such as zero-valent iron walls, for example, wouldn't be that useful. Slide 4 here briefly describes our technical objective, and that's to understand how hypersaline potassium permanganate invade a heterogeneous porous media and tends to remain in place. So the idea there was we were trying to look at how a dense fluid that was a treatment fluid at the same time would move in a system and then hang around in the system. The second part here was to examine the possibilities of using biopolymers and gels to essentially slow down the rate of migration of permanganate and really control the behavior. Slide 5 here just essentially summarizes our approach. Our approach is predominantly experimental, but we do use mathematical modeling to a great extent. And essentially, we're doing all of these to look at hypersaline potassium permanganate fluids invading heterogeneous style porous media, and tending to try to make it remain in place because of density effects. And the second part really was to look at biopolymers and gels, and it turned out that we focused on inorganic gels as a primary approach. Slide 6 here briefly outlines the next few slides that I'm going to talk about, and in terms of the background and the scientific basis for the method. Our approach that we use and have extended here in this project really revolves around 4 components. First of all, the tendency for chlorinated solvents to be oxidized by various types of powerful oxidants like potassium permanganate and other things. We also take advantage of controlled release technologies that we've had experience with in the past. And I'll have a bit more to say about that in the next few slides. We use theory of variable density flow. So one of the advantages here in this method is that we're trying to move our treatment fluids down vertically through the system, and we use density to drive that. We also, with Part 4, are interested in potential additives that can change the viscosity of the fluid, especially once we get it into place, and ultimately form gels. So the first three of those components we've studied in the past. Part 4 tended to need additional study. So the cartoon there at the bottom shows a quintessential DNAPL plume with a source area at a disposal site there shown in yellow. So the yellow and red are pure phase DNAPL essentially. The brown is a dissolved plume there essentially, and our focus is going to be at the downstream end. So we're not really mucking around up in the source area where there's a tendency for a greater amount of pure phase material to be found. We're focusing on the dissolved phase contaminant plume and so on, with a plume control mentality there. Slide number 7 shows some of the work that Dr. Lee and I did in the past, and that we used as a building block here. Very briefly, we've always been interested starting in the mid-2000s about the ability of control-release systems to work. And our first control-release systems, you can see that first picture there in the middle, is essentially permanganate candles where we take wax and we embedded potassium permanganate crystals in there. And as the little column experiment shows on the right, we ended up with an ability to slowly release potassium permanganate. And the pictures at the bottom show how this might work in practice. So this was a large tank experiment that we created in Korea with support via various Korean agencies. And the little picture at the right shows 3 lines of these candles installed, and then we ran a TCE plume through this and looked at the ability of the system to remediate. In terms of variable density flow, this picture that we have here on slide 8 is really designed to show how, for example, a dense fluid like potassium permanganate tends to sink and underride. And that was one of this very simple column experiment here, or flow tank experiment, was one of the motivations for our initial proposal. And what it tends to show is that, well, potassium permanganate does sink, and it can flow through a system without expanding a dissolved plume and so on. So this was a nice complement, and it built on our research in the past. Slide number 9 really talks about a new thrust, and that was the idea of using gels to reduce the mobility of potassium permanganate. So the idea was that with the second part of the study was to create in-situ slow-release systems, like we had, as the picture showed, some slow-release systems that we made at the surface and deployed in the subsurface. But with this project, we were mostly focusing on trying to create these in the subsurface. And again, this complemented this slow-release type work and so on. And initially we started out with a biopolymer approach, hoping to find among the biopolymer family something that really had the ability to not be degraded by potassium permanganate and so on. But we weren't very lucky in that respect. So we tended to move on then and worked with organic additives, and they worked very well by and large. And I think that's one of the successes of our project. And we used 2 components really and looked at 2 approaches, one based on potassium sodium silicates that Dr. Sulpucker and I focused on here at Ohio State, and colloidal silica, which Dr. Lee and his students there at OU tended to use as well. So slide number 10 then begins our discussion of the results, accompanying tasks 1 and 2 essentially. And I think you'll see that the experimental results that we've kind of produced here and produced for this slideshow here try to show that indeed many of the kind of ideas and demonstrations do make a proof of concept that we're pretty happy with. So one of our early approaches then was to use our large tank, and there's a picture of our large tank there at the bottom. And the purpose of this was really a proof of concept to show and illustrate how, for example, one could add potassium permanganate to a flow system high up in that system, and then count on convective mixing with the ambient flow. So in other words, what we're going to see in those little red arrows on the flow tank kind of show you, that's the idea that if we put a dense fluid in that upper unit, and it's the thin clear unit there, that the density will cause the potassium permanganate to move deeper down into the flow system, gradually mixing and so on. And if that deeper unit at the very bottom of the tank was contaminated, then this potassium permanganate we put in the system would slowly bleed in there over a longer period of time. Slide 12 then sort of shows you one of the several flow tank experiments we did. And this is an example of a heterogeneous media. And if you look at the flow tank, the black unit toward the top of the tank there near the very top is a permeable coarse layer. And it's a sort of an isolated layer in which we added the potassium permanganate with the idea it couldn't flow anywhere, and so we kind of constrained it that way. The medium gray layer that constitutes most of the tank is kind of an intermediate fine layer. It's a lower K unit. Then the white unit in particular is a clay layer that we produced by mixing bentonite with very fine glass beads, and so that has an extremely low K. So we created a system that had both coarse units, fine units, and very low K units. And we added then to begin this experiment sodium chloride as our dense fluid, standing in for potassium permanganate, and we used a dye then to trace the progress of the variable density flow. Then the injection occurred there. There's a small star up there in this spot that sort of shows where things were injected, and that's kind of right up around there. And we injected for 18 days and then looked at what happened for 37 days once the injection stopped. We can't show an animation, but we will, for example, show you some, step through some slides here to show you some things like penetration into the low K unit, mixing, and slow bleeding out as well. Okay, now this is the tank at the start of the experiment, and I'm going to create a kind of a crude animation here by just quickly stepping through. So slide 13 is nothing is happening. We're at day 2. You can see we've added the faux potassium permanganate solution into that lens, and you see fingering and downward migration. And day 6, you can see it's moving further down. And you can see that we managed to create a bowl here by our plume shape. And the main thing is then that the idea that finally in the deeper unit down here, that's where potassium permanganate then is going down and mixing with that ambient flow that's coming in from the left side here as the experiment is proceeding. And this was the idea then that we could store the potassium permanganate in these finer low K units and then slowly release them in the deeper units. So day 18, you can see we've got a lot of flow in that deeper unit now. And then at day 18, we shut off the injection now, and I'll show you after day 33, the material is still slowly releasing into the deeper unit. We still have some inflow here at different spots here, and so the system is still slow releasing, and that was the concept that we were trying to do. At day 38, similarly, things are dying out here, but you can still see in about the same spots we do have inflows as well. Day 50, we still have things, and when we finally shut this off at about day 50. And after that, we tried to carry out some simulations to do that, and Dr. Salpuker did many of these simulations, and the results ended up, we were happy with the results. We used a variable density code called Mitsu 3D, developed here at Ohio State by one of the professors in the neighboring office here. And the results were good. Now, what we've discovered as we're doing the simulations of these variable density experiments with instabilities is that it is extremely difficult to actually simulate the details of what's going on. These are highly nonlinear systems, and just small perturbations in the K field or whatever causes the fingering to go off in different directions. And so, our experience in this respect kind of echoes other more recent things that we've seen in the literature where people have lamented how difficult it is to actually, do simulations of these systems. So this sort of shows the simulations there, and it captures the spirit of things. This is the simulations then after 2.5 days, 18.5 days, 17 days, and the reason I said we simulated a bull, you can kind of see the simulations kind of look like a bull that kind of has the same kind of idea. And it confirms the ability to simulate broadly what's going on, but we're having difficulty simulating the actual instabilities and fingering that go on. Slide 23 then is a summary of the observations then of this experiment. And I think it's clear that the kind of geologic conditions, hydrogeologic conditions of hydraulic conductivity that we set up here did create conditions for slower release, and that's what we were trying to do. We halted the experiment after 55 days. We had backflow and so on. But it was extremely difficult to flush things from low K zones. And the idea that very low K units actually ended up gathering up some of this fluid and really slow releasing it via diffusion over a very long time. So we didn't have many places where we had very low K deposits, just a few examples there. But in these units then, these things essentially bled the tracer for very long periods of time. We saw density-driven flow, and this experiment provided visual and theoretical confirmation of this slow release idea and mixing of potential treatment chemicals. Now, task 2 had us move into the arena of starting to look at gels and polymers and so on. And, we took a quick look at biopolymers up here, like chitosand as one example. But we quickly moved to inorganic things like potassium, sodium silicates, and colloidal silicates. And these worked very well for us, and we're going to recount our experience with this as well. And so we also, along the way, examined the potential of some of these geopolymers that we constructed to serve as conventional slow-release systems. This sort of fell out of some of the work, and we just continued that. So slide 25 then, sort of outlines our subtasks, and these were part of our regular effort then. And what we're going to talk about next is, the use of sodium silicate grouts, and these things really, we didn't discover them. These have been often used in geotechnical applications and so on. They typically are constructed of 3 adjustable components: silica, soda ash, potash, water, and so on. And they have many adjustable parameters in terms of the way you actually create the solution. You can vary different solutions, such as the silica to alkali ratio, the temperature, and so on. And but basically, as you can drive these things to produce siloxane chains, which are organic functional groups that start out as a chain and then later reform as a 3-dimensional network. And I'm going to turn it over now to Dr. Sulpuker to continue. This was much of his work here, as was most of it on our side, dealing with this particular part. So he can have controls and keep going here.
Okay, thank you, Frank. Next slide. Okay, so there are different types of silicate solutions depending on the silicate to alkali ratio. You see 2 graphs here. The source is from PQ Corporation website. On the left-hand side, you see viscosity change with respect to specific gravity, and there are different silicate solutions with changing silicate to alkali ratio. And this graph on the left shows the sodium silicate solutions exhibit increased viscosity when water is removed. On the right-hand side, again, the viscosities of the sodium silicate solutions is a function of silica to alkali ratio at constant solids. Again, viscosity increase as the weight ratio becomes either more siliceous or more alkaline at a given solids constant. So it shows how it is easy to adjust the viscosity of the sodium silicate solutions by changing either the sodium oxide silica to sodium oxide ratio or solid to liquid ratio. The next slide shows here that actually the silicate solutions are alkaline solutions with high pH, and with the addition of acid lowers the pH of the solution and causes polymerization and gelling. And this graph shows you the sudden increase in the viscosity of the silicate solutions, and basically you develop a non-flowing silicate gel. The next slide here, in addition to the silicate solutions, we also explored the use of inorganic polymers that are able to resist oxidation by permanganate, because permanganate is strong oxidant, oxidizes pretty much anything. So we were concentrating our efforts on geopolymers, which are amorphous to semi-amorphous crystalline silicate aluminate mineral materials. So our focus on here is to incorporate potassium permanganate granules into the geopolymers, and then create some sort of a slow release material. Here I would like to give a little bit details about how a geopolymer is produced. The main ingredients are metakaolin, which is produced by calcination of purified kaolin, and also sodium silicate solutions, which about 38% solids with a silicate to alkali weight ratio of 3.22. And we activated the sodium silicate solution by adding sodium hydroxide pellets, and this was a necessary step for the reaction between metakaolin and sodium silicate to take place. And we prepared 3 different samples by adding different amounts of potassium permanganate into the geopolymer batch, and the resulting silica to alkali molar ratio is about 2.8. So samples are tested by separate column leaching experiments. So the first sample has about 10 grams potassium permanganate. The second one has about 35 grams of potassium permanganate, and the third sample is about 50 grams of potassium permanganate. So this figure shows the change in permanganate concentrations in column discharge and percent permanganate release through time. So you see that permanganate concentrations initially high, but declined rapidly over 8 to 19 days. And release rate and lifetime depend on initial potassium permanganate plus other important processes. This one, the sample one, which has 10 gram potassium permanganate, reached its lifetime about in 7 to 8 days. The other two, it took about 18 to 19 days to reach their lifetime. So here you see some scanning electron microscope pictures from the geopolymers after they have been flushed by water, and you see the creating potassium permanganate depletion created some secondary porosity in addition to the original porosity inhabited by the geopolymer itself. So flushing samples created these large pores due to the dissolution of potassium permanganate, and the smaller pores, which may not be clear here, are due to the structure of the geopolymer. So we used a method of analysis from the pharmaceutical industry, which has been used for many years. So pharmaceutical models usually have diffusion as the primary mechanism following fixed laws with constant diffusion coefficient. So theory provides for deviations due to other processes, and like here you see an equation showing the fractional release of the chemical, which is permanganate, is equal to kinetic constant and time, and there is a release exponent indicated by n. So if the process is purely Fickian diffusion, we expect to see the release exponent equal to 0.45. But here we figured that this release exponent is greater than 0.45, indicating that there is more things going on other than pure Fickian diffusion. So accelerated release of potassium permanganate via fast transport through secondary pores created by dissolution of potassium permanganate grains is the additional process in addition to pure diffusion.
Okay, now we'll shift gears a little bit and talk about colloidal silica. And the colloidal silica excuse me, work was done by Dr. Lee and his students there, and so I'll let him start here. We're on slide 33.
Okay, so our study focused on first actually testing the compatibility, chemical compatibility and miscibility of available gels. So we tested Gelation first, which we found not compatible. And then also we tested aluminum silicates, and that was chemically compatible with permanganate, but you can't just mix permanganate with aluminum silicate. Basically, a permanganate solution is just sits on top of it because it has such a tight structure, not much room to have that permanganate solution in its structure. So the only two gels left for us to then pursue were silicates and colloidal silica, and in our study focused on colloidal silica. The objectives were to develop slow-release permanganate gel using colloidal silica as the gel material, and then to characterize and also optimize the gelation rates or gelation kinetics, how fast gelation occurs. And then gelation occurs through soil gel process. So we use that process of colloidal silica, and then we characterize the controlling factors for gelation kinetics. And then we try to optimize gelation lag times. Here, lag times means how long this mixture of colloidal silica and permanganate solution, dense permanganate solution, can flow after the injection without being gelated, so that it can spread away from the injection walls for a while, and then gelate to become gel. So that time is what we call lag time. So we wanted to make lag times longer or shorter, and we wanted to find the way to control that lag times as well. And then if we go back to this one, and then we also tested the release characteristics of the gels, colloidal silica permanganate gels, both in column test, just in flowing water, and also in a column filled with sand to see how it moves through the pores in sand, and also how it gelates and releases in sands. Okay, so here are two graphs that we generated. The one on the left is the how viscosity changes with time when we, for example, mix colloidal silica with dense permanganate solution. So as it's shown here, the viscosity stays the same, sort of same for, in this case, about 100 minutes, and then just picked up and started increasing rapidly over a very short period of time. So that was typical pattern that we see the gelation occurs. So it doesn't change for a while and then rapidly increases, rather than just gradually or linearly increases with time. And then the one on the right, the graph on the right, shows the gelation lag times, how it changed with the potassium permanganate concentration in the solution. So as we can see here, higher potassium permanganate concentration resulted in a much shorter gelation lag time. So if it's higher than 20 milligrams per liter, then gelation lag time was basically less than hour. And then when it becomes low, 18 milligrams per liter, it was about 1.5 days. And then for as it goes lower and lower, it becomes more and more sensitive. So with just only slight differences in permanganate concentration in the lower end, we see a large difference in gelation lag time. So the longest lag time we achieved was 13 days. It stayed same for 13 days, and all of a sudden it formed gel. Okay, so then we moved on to post media phase. So those glass columns are about 1.5 meter long glass column. So we filled it with sand and injected a mixture of potassium permanganate and colloidal silica, and those photos show how the solution moves through the pores and also how the gels are formed. So the second from the bottom, the photo, the second from the bottom shows the gel form at the bottom of this column. So we twisted the column to show the gel form there. So it initially sinks through the pore and then form the gel. So if you look at the graph on the right, it shows the release pattern of permanganate from the gel formed in saturated porous media with flow. So similar to the graph Dr. Stolper showed, the concentration increases, and there's an initial peak concentration, and then it rapidly decreases and sort of stabilizes. And in this case, the release lasted for about 100 hours. So we found that we can control the gelation length times by changing permanganate concentrations, and then we observed the formation of gel in porous media, saturated porous media with flow, and then the release of the permanganate was slow, and these results were published in two Chemospheric papers, and we're actually continuing on this gelation test in sand using a different colloidal silica materials with different colloidal silica concentrations, and also trying to do this in 3D using a flow tank as well.
Okay, thank you. You probably need to pick up the pace. We got about 5 minutes left according to my time here.
So similarly, we try to do the same thing with the sodium silicate solutions. We varying the concentrations of sodium silicate solutions and certain acids and acid salts. It's possible to manipulate the gelling time of the silicate solutions. So we used sodium silicate bicarbonate mixture, which has initial low viscosity, but it didn't. The viscosity didn't stay as low. After about 200 minutes or so, the viscosity started to increase, and then you see in this slide the viscosity increased fairly quickly after that. I would like to give a little bit more information about that combination. Sodium silicate solution that we use has a pH about 11.3, quite dense. Specific gravity is about 1.39. Viscosity is about 180 centipos. But we diluted this silicate solution by about 58%. And we prepared also sodium bicarbonate solution, and we diluted the concentrated bicarbonate solution by about 53%. So we mixed the diluted sodium silicate solution and the diluted bicarbonate solution to about 50-50% proportion. So the initial viscosity is about 2 centipos, which is good for injection purposes, and the gelling time of this particular combination is about 1 hour. So the next slide shows us our trial of this gelling solution in a big flow tank. Here you see the setup. The black color represents the coarse layers and lenses. White color shows the clay-rich layer, and the gray layer shows the fine layers. So we injected the gelling silicate solution into that high conductivity layer at the top, and this high conductivity lens in the middle. So we added also 300 milligrams per liter tracer rhodamine into the gelling silicate solution. This is how it looks like after 2 hours. At this time, most of the silicate solution was gelled, and you see the development of the instabilities under the coarse lens, but there is no development of instabilities in the clay lens because there is no diffusion into the clay lens at this point. So here there's more bigger instabilities develop under the coarse lens, and there's intrusion into the underlying coarse layer, and again there's a slight diffusion at this point after 1 day into the clay layer here.
So by this time everything is gelled up there in that system.
Yes. And after 1 week we see quite rigorous mixing under the coarse lens, and the underlying coarse layer was invaded with the dense solutions. At the top there is a little bit of diffusion into the clay layer, but most of the solutions, dye solutions, are moving upwards due to the interaction with the background flow. By the way, background flow is from left-hand side to the right-hand side. And at 2 weeks, we still have some gel at the coarse lens in the middle, and there's a lot of mixing took place under the lens. At the top, you see the boundary between the gel and the coarse layer, but most of the dye is interestingly moving upwards due to the interaction with the background flow. Here we tried another experimental approach using potassium permanganate with gelling silicate solutions, and we used a smaller flow tank. Here again the black color represents the high conductivity layers and lenses, and white color represents the clay rich layer. We did our injection into the coarse lens here and into the coarse layer right at this point. And this solution includes 2 weight % potassium permanganate. This is right after the injection finished. You see dense solutions, potassium permanganate rich dense solutions are sinking under the coarse layer, and there is a diffusion into the clay rich layer at this point, and you see the oxidation rim is taking place due to the oxidation of the glass beads due to the strong potassium permanganate. And the next slide shows the situation after 4 hours. There's more bigger oxidation rim and more greater diffusion into the clay lens here, and here the solution is gelled at this point in the coarse lens and at the coarse layer, and you see the development of strong instabilities and the sinking of the potassium permanganate rich dense solutions towards the high conductivity lens in the middle. So after 10 days, most of the permanganate was gone from the top of the clay layer. It's either all diffused into the clay layer, and some of it is used in the oxidation of the glass beads. And beneath the coarse lens here, you see the boundary between the silicate gel and the background coarse glass beads, and there's still diffusion going on here at this moment, and potassium permanganate is diffusing out and sinking downwards towards the high conductivity coarse layer in the middle. After 20 days, there is not much left in the gel. There's still, you see some pinkish color due to the remaining potassium permanganate, but most of them is either evacuated from the system or some of it used in the oxidation of the glass beads.
Okay, thank you. There is one more section that I put together here for our talk, and I've run out of time here to describe that, but it's here for you. Basically, we work together with some co-workers at University of Dresden and UFZ in Leipzig, Germany, and they were really interested. These are some very fine numerical analysts, and they were trying to work on schemes to model this whole system. So in other words, transport of a dense fluid with gelation. And you know, here's the equations that I set up. I'll just quickly pop through that. You know, there are functions here such to build in the gelation's chemistry, sort of, that the idea there's a threshold, that viscosity increases with time, and so on. Dr. Sulpucker ran some test cases where we changed the gelation times, so we had a quick gelling thing over here on the right. Then we had other things that gelled much slower. And, you know, so the first experiment at the top is the experimental stuff. At the bottom is the numerical things, and it worked extremely well, and so it captured that. Then with this other system, because it didn't gel so far, this blob we put in sort of sank with time and then gelled at the bottom of the tank. And again, the model found that behavior as well. So that was a good result. So essentially, I think in terms of conclusions and summary, I've got a couple of slides. I'll just say some things here. I think we've shown that the mixed convective systems, that is the dense treatment fluids with contaminated groundwater, could in a certain style of system provide a slow release mechanism. We need a fairly unique geology to accomplish this, low K units providing a slow release mechanism, perhaps very fine low K units to sequester things, but I think the idea is certainly viable. I think the experiments and computer simulations show that with the geopolymers, we were able to actually emplace potassium permanganate. It tended to plug up the medium. It slow released with time, and so on. So it was a very interesting material. With the study, we were able to manipulate the gelling time to some extent, and that's the one area that needs additional work, I think. So we were pleased with that. We've outlined a transition plan here. We've interacted some with people at Hill Air Force Base. That we tried to develop a test in the field to some extent. That didn't really work out because of budget limitations. We're looking with other partners, especially in Korea and China. We've, in terms of participation with the user community, I did yeoman service in editing 3 chapters of the SRP oxidation book, or reviewing them, not editing them. And we've tended to interact with Keras Corporation, who are the permanganate people, in terms of that. And you know, they've been helpful in sponsoring some of our student travel. I've done a webinar for them, and so on. So we have some participation. Here's our publications. It doesn't represent all of them. We have some works in progress right now. But you can see that we've been active in terms of things going out in various journals, fairly high impact factor journals. And I think that this could be it. Okay, that's it. So thanks everybody. I'm sorry we ran a little long.
Oh, that's fine. Thanks, Frank. We have time for a few questions. If anyone has any questions.
Andrea, I have one.
Sure.
In terms of, like, I'm thinking about the field application of this material. Can you see any difficulties in injecting this mixture in the field?
Well, I think we're in pretty good shape there. We've you know, the sand tank material, it's relatively permeable, but the sand is very fine grained. So the material we inject is extremely watery. I think in our case, the sodium silicate viscosity of that compound, when it's mixed with potassium permanganate, so the potassium permanganate is dissolved. The other thing, so everything is in a solution when we put it in there. The viscosity is perhaps 3 times the viscosity of water, so it's extremely watery. But then, so it's injectable, and then after it's injected, it takes upwards of 20 minutes perhaps to become a gel. We think there are ways to lengthen that. Maybe Dr. Lee could say a little bit. He's had longer, obviously, lifetimes before gelling occurred, and with colloidal silica, and then it offers a slightly different, because they're particulates. Maybe NSOC could say a few words.
Yes. So the gelling lag time depends on the permanganate concentration and also the concentration of colloidal silica in the gelling material. So more colloidal silica, then it'll take less time to gel, but also, on the other hand, it can last longer. The release duration can be longer because then the material is denser. So there's pros and cons if you want to make it lag time longer than the duration of release might be short. If you make the duration lag time relatively short, then you can make the release duration longer. So it'll depend on the field settings. So depending on the size and how many injection wells we can put in there. So if we have only a few wells, then we probably will need longer gelling times. If we have more wells, then we don't need such a long duration lag time, so we can increase both permanganate concentration and also colloidal silicate concentration. It will depend on those settings.
Thank you.
Frank, I can add a couple things.
Okay, sure.
You can mix the silicate solution, diluted silicate solution, and the acidic solutions at the injection point. Or you can first inject the silicate solution and then inject the acidic solution, so the mixing takes place under the ground. That's about it.
Okay, thanks. I think that's all we've got on that.
Okay.
I guess I've got a question. This is Chuck Grower with Corps of Engineers.
Yes, hi.
Is there, I'm just trying to get it straight in my mind, the advantages of having something that gels versus something that just naturally diffuses into clay and then is slowly released naturally. Have you looked at comparing that, whether how much advantage is there to trying to produce something that gels versus something that naturally diffuses and then just slowly releases from a clay layer?
Yes. So those were the second case that you talked about. We didn't study that particularly extensively, but that was the concept, that either by the fact that the hydraulics of the system would tend to slow things down, and then if there are low K units, then you get additional slowdown by diffusing into lower K units and diffusing out. So, diffusion as a transport mechanism really has, advantages of providing lifetimes. So I think that's pretty clear. To answer your question on what the additional advantage is, that we could see, for example, using the second approach where we put a gel in there as a second component, and this perhaps would work in a system where there was a lot less finer grain units. And what the advantage is that if you design the gels properly and inject them high up, they would start to sink and they would gel. So the idea is then that doing a fairly big mass of this, the gel actually hangs around a lot longer, and in effect then, it really, as the material gels, it creates the same process such that you have a low K unit that has diffusion as a release mechanism. So that's when you place the gel, that's what you're doing. We didn't show you here, but Dr. Sulpucker, I mean, we have some diffusion measurements of potassium permanganate inside the gels, and they're probably an order of magnitude less than water. So actually doing that sort of creates the kind of environment you're talking about. I hope that answers your question.
Yeah, that helps. Thank you.
Any other questions?
Yeah, this is Marvin Unger from CERTA PSTCP. Frank, great presentation, gentlemen, really good. I know this was a limited scope, and this is under CERTA, but there are some things that using ISCO is tricky, and it's a bit of an art form. The three things there's 3 points to the question, and that is, one, regarding secondary water quality, most particularly pH and salts. One, is this technology going to impact the concentration of salts as well as impact the hydrogen ion concentration in terms of pH? Or if not, will the converse of that, is there a possibility that depending on the environment, let's say you had high salts and a very low pH, is this technology applicable for certain scenarios like that? The second part is, we know that permanganate can be compromised as part of its oxidation potential in subsurface environments that have high organic matter. My question would be, might there be a critical organic matter concentration, at which point this technology is rendered no longer effective? And then the last point to that is, doing a lot of talking about gels and grouts, and we haven't even discussed the possibility of the formation of manganese dioxide nodules here. Is there any belief that this technology may actually impact the redirection of groundwater flow? I know that was a lot, but these things were on my mind. It was a very good presentation.
Okay, thanks. I guess I'll deal with the middle or the third question first, and that's the issue of utilization of oxidant by organic material, and I mean that's an Achilles problem of all permanganate kind of applications. Clearly, ours isn't really any different in that respect. I mean, we need to be able to have enough permanganate left over after sort of natural utilization goes on to do something. And I mean, nothing that we've really done has, changed that issue with respect to this method. So it still has that same problem as the other methods have. In dealing with your last question, we really didn't focus on that generation of manganese, water quality style issues. So, clearly we're aware of it, and again, that's one of the concerns with permanganate in general. And we don't think anything we've done really it changes the state of knowledge with respect to that in terms of permanganate technologies, right? So again, if there's a problem that occurs, then we're stuck with that same problem. We don't think we exacerbate it in any way or reduce it in any way. So I think our sense is that it's something to be cautious about, but the mobilization tends to be quite localized, and the system, I think, once you get away from the site of destruction and so on, restores itself and goes kind of back to a more oxic equilibrium kind of structure typical of groundwater, where naturally those things would be kind of low. But we haven't done anything. to answer your first question, I think also we to create the variable density fluids, we're putting potassium permanganate in there. The salinity will increase. You end up, with that reaction, with depending on how much things you destroy and so on, you generate chloride. But there is a density effect. Now, I think the idea is that we're trying to create a reactive barrier. So, we're not trying to do huge floods like some of the trials that went on. For example, that test in Florida where there was like 500,000 gallons of permanganate, or some huge number of permanganate solution was injected, and there was like water everywhere. So I think yes, it's an issue that water salinity could be impacted, but I think we could see that if we're careful and strategic, we're trying to locally control things. And because we're at the downstream end of the plume, we don't have to overdose with the treatment chemicals, because we're just trying to get enough permanganate in to knock out, less than 100 micrograms per liter TCE and so on. So I think there's not a need to go crazy with this technology, like people might be tempted to do further up where you've got huge mass distributions, if you understand what I mean. And I think, in saline environments there would be some strategic advantage to this. I mean, taking away the need to really worry about major ion chemistry and secondary water standards and so on is an advantage. And so I hope I've kind of touched on your questions.
No, you have, Frank. Thank you very much.
Any other questions? Okay, well, thank you, Frank, very much for taking the time to give us this final presentation. It is very helpful to us, and we do appreciate your efforts in this regard.
Okay,